Welcome to the lecture on multi-degree of freedom system. Today we will discuss the concept of static and dynamic coupling. So as we know that we can we have defined the degree of freedom. So n degree of freedom system, if it is a multi-degree of freedom system, so it needs n independent coordinates to represent its configuration at any instant. Generally, we take these coordinates from the equilibrium position. For example, we take from center of mass. We can select any other set of degree of freedoms. For example, if we have, there is a lathe machine and there is a model of this machine. So this machine, it has headstock, tailstock, there is a bed and this column. So we can assume a model of this system, and so here there is the elastic stiffness of these columns. There is this bed, okay, and we have the center of mass or center of gravity of this system here. So we can, because the motion of the system can be in linear as well as in angular directions. So we can select a degree of freedom passing through center of mass. So we can take the motion of here xt, that shows the motion of the center of mass, and the angle theta, the rotation, angular motion of this system. We can take another set of degrees of freedom, that is x1 t and x2 t. So these are another set of the degree of freedoms that can represent the system's configuration at any instant. Also, it is possible that we select a degree of freedom that is not on CG but some other point, and from we can get the configuration in terms of this point. So we can assume some point and its motion in linear and angular motion. So we can take that set of coordinates. So all these sets, they are known as generalized coordinates, because these coordinates are it depends that they are our choice. They are not some property of a system. They are our selections. We select these coordinates, and we so for example, if we select this coordinate, so we have here this center of gravity and its motion xt, and then theta t, we take the angle with respect to this axis. So what happens? So it is a system like this. So we have this system, and this system is moving here, okay, here with x t, and again it is rotating here with theta t. So this is theta and this is x. Now if we have these springs K1 and K2 and this distance is here, this is L1, L2 here. So the forces acting at this point or this, because the total deflection of this spring is x minus L1 theta, because this is theta and here this is theta. So x minus L1 theta and into K1, so that is the force that is acting on this. Now on this spring, so the net displacement of this spring is, so it is x plus this, that is L2 theta, so it is x plus L2 theta and multiplied by K2, so that is the force on this system, and the mass of this system is m and the moment of inertia is j. So we assume that the mass of this system is m and moment of inertia j at the center of mass. So now we can write the equation of motion of this system. So mx double dot equal to the forces. So these are the, so this is x double dot and that is minus, so this is opposite, so it is minus K1 x minus L1 theta and this is again opposite, so minus K2 x plus L2 theta. So we can rewrite this equation mx double dot plus K1 plus K2 x minus K1 L1 and this is plus K2 L2 into theta. So this is equation number 1. Similarly, we, for the another degree of freedom, that is the rotation or angular motion. So we take, so we have moment of inertia as j and theta double dot. So now we have we take moment about this point. So we have this is the force and that distance L1. So this is distance L1 and this is L2. So this is giving a moment about this point, okay, and this theta dot double dot is positive as a clockwise and this is moment in the same direction, so it is K1 x minus L1 theta into L1 and this is in the opposite, so it is minus K2 x plus L2 theta into L2. Now we can rewrite, so it is K1 L1 minus K2 L2 x and minus k1 L1 square. So it is minus k1 L1 square theta, and this is minus k2 L2 square theta, and if we take it is like this. So j theta double dot equal to j theta minus k1 L1 minus k2 L2 x plus k1 L1 square plus k2 L2 square theta equal to 0. So this is equation number 2. Now these equations 1 and 2 we can assemble in form of a matrix. So if these equations 1 and 2 we assemble, so it is m 0 0 j, and this is x double dot theta double dot, and that is equal to plus we have another matrix, so k1 plus k2 and minus k1 L1 plus k2 L2 so it is plus k1 L1 theta, and this is minus so it is minus and it is minus, and this is minus k1 L1 minus k2 L2, and this is minus k1 L1 minus k2 L2 and plus k1 L1 square plus k2 L2 square. This is x and theta, that is equal to 0 and 0. So we have arranged so we have this equation, first equation, so k1 plus k2 x, so m x double dot, and this is 0, so plus k1 plus k2 x minus k1 L1 minus k2 L2 theta equal to 0 and here j theta double dot minus k1 L1 minus k2 L2 x plus k1 L1 square plus k2 L2 square theta equal to 0. So now we can have only the matrix form. So now we see that from this expression, this matrix expression, so it is so this is the matrix expression, and from this matrix expression we see that in this equation, if we write when the equation in the first equation, that is the linear motion degree of freedom, we have also this theta term, and therefore the system is coupled. And similarly in the angular motion there is the x, because minus k1 L1 minus k2 L2 x. So this is, however, there is no x double dot, in x double dot there is no theta double dot, okay, but here x and theta they are there is. So when there is such a situation, so we call it static or elastic coupling. Elastic coupling. But it is not a this system is only static coupling, not the dynamic coupling. There is no any coupling of the acceleration terms. However, if we want to uncouple this system, we have to make these terms 0, because if it is 0, the theta component will be 0 in equation 1, and this is 0, then x component will be 0 in the theta equation. So therefore for uncoupling k1 L1 minus k2 L2 equal to 0, this is the condition. Now we take the another example, I mean another set of degree of the coordinates, another set of degree of freedoms or general coordinates. So here we can see we have now here is a point P, and we have selected the yt, that is the linear motion of this point, and angular motion theta as a generalized coordinate, and now we will study this system. So now we have a system like this. So the same system, here is G, and we take a point P that is at E distance. Here the distance is E, and here we have these springs, and here we have these spring, that is K1 and K2. Now we take this distance, here this is L1 dash and this is L2 dash. Okay. So from point P to this spring, okay, there is L1 dash and this is the L2 dash. Now again we have we have displaced this system, so linearly as well as angular motion. So we have here yt, here we have P, and this P, so we have P, this is G, and here is M and J, the mass M and J. So mass M is center, this is center of mass, and J is moment of inertia about this point. Now we have this Y, and this is theta, and here we have these spring forces. So now we have these points L1 dash and this is L2 dash. So we can write, now we should understand that when we take it here, now we write equation of motion. So my double dot equal to, so here it is k1 y minus L1 dash into theta, and here it is k2 y plus L2 dash into theta. So because we are here y minus, because it is y minus, and this is y plus L2 dash theta. So my double dot, so acceleration here is, this is y double dot and this is theta double dot. So my double dot equal to, so this is opposite, minus k1 y minus L1 dash theta minus k2 y plus L2 dash theta. However, there is theta double dot, so there is the inertia force, that is m times e theta double dot. So it is and inertia force is opposite, so minus m e theta double dot. So that is equation number 1. Similarly, for the angular degree of freedom, so Jp is the moment of inertia about the point P. Okay, so Jp into theta double dot equal to, so now about this point theta double dot is in clockwise, so this is giving clockwise, so it is k1 y minus L1 dash theta into L1 dash, however it is giving opposite, so minus k2 y plus L2 dash theta into L2 dash. Again there will be an inertia moment due to the degree of freedom y double dot, so that moment will be m y double dot is the inertia force and into E, because this distance is the distance between these 2 points E, so the moment is minus m e y double dot, because m y double dot into E. Now we can the equation 2. So equation 1 we can write again as m y double dot plus m e theta double dot, then y terms, so we have k1 y and k2 y, so it is k1 plus k2 y, and here k1 L1 dash theta, and this is k2 minus k2 L2 dash theta, so it is minus k1 L1 dash minus k2 L2 dash theta equal to 0. Similarly, equation 2 can be written as MEY double dot plus JP theta double dot, then y term, so it is minus k1 L1 double dash and here k2 L2 dash, and that is plus, so it is minus k2 L2 dash y, and then theta, so theta term is here k1 L1 dash square, so it is plus k1 L1 dash square, and this is k2 L2 dash square with minus, so plus k2 L2 dash square, and it is theta equal to 0. So now again we can write these two equations in matrix form. So we can write them as m MEMEJP y double dot theta double dot equal plus K1 plus K2 minus K1 L1 dash minus K2 L2 dash minus K1 L1 dash minus K2 L2 dash, and here K1 L1 dash square plus K2 L2 dash square, and this is y theta and equal to 0. So we have written the equation in form of a matrix, and now we see that now for this matrix there is no that is not diagonal, so there is the off diagonal terms are non-zero, and we can see the effect in the equation that the acceleration terms are coming in the equation, each equation. So here in equation of y motion there is theta double dot term, and in theta double dot there is y double dot. So this is called coupling, mass coupling, or that is also dynamic coupling, and this is, as we have already discussed, this is static coupling. So here we have static and dynamic both coupling. Static coupling from here due to the stiffness matrix, and the dynamic coupling due to here the mass matrix. Now if we take a general system that is having the mass, damping and stiffness matrix, so if we have system like M x double dot plus C x dot plus K x equal to 0, so this is a system. So if the stiffness matrix is not diagonal, then the system has elastic or static coupling. However, if the damping matrix is not diagonal, it has a damping or velocity coupling. If the mass matrix is not diagonal, the system has mass or inertia coupling. These two couplings due to damping and mass matrix, that is called the dynamic coupling, and this is the static coupling. So here we discussed the static and dynamic coupling. So we stop our lectures, and I wish you all the best for this course and the examinations. Thank you.